Good morning, guys. Today I want to kind of show you the where this idea of Taylor polynomials and Maclaurin polynomials comes from. The mathematics behind it is really beautiful to me, and it's kind of really a cool idea. And so, although you don't need to know the background to actually do the work, I do want to at least take the time to show you how it came and how it came about. So here's what we're going to do. We're going to talk about the problem that led to this whole idea. Because most of our mathematical things come from a problem that somebody was trying to solve. All right. So here's the deal. If I wanted to find the value of sine 0.15, how would you do that without using a calculator? In fact, how do we even find this value to begin with? How does your calculator know it? Okay. Now, when I was younger, I used to have to use tables to look this stuff up, but I mean, I don't know. Where does that come from? What about this? What about, well, I want to raise, but how about e to the 0.07? How do you raise something to the 0.07 power? And although I do know a way to do this, to manually calculate it, how do you do that? Well, the problem is these are hard things to calculate. And so what we would really like to do is to approximate these with a function that is easy to calculate. And in general, a polynomial, not n up there, but n down low, an nth degree polynomial is great because you just have constants and variables to powers. And even if you're having to do this, by hand, you can do this. So if we can find a polynomial that approximates our function, then we're going to be able to calculate it and we'll be able to get pretty close to what we want to know. But how do we come up with this polynomial? That's the question. Well, we have to have some rules. And here's where it comes from. First of all, we're going to pick a value c. And so let's say that we have, let me just clear this whole thing. Let's say that we have our generic graph, and it looks something like this. And here is c. And there is f of c right there. All right, what we want to do is we want to approximate in some neighborhood around here, okay? So in some neighborhood around C, we want our to be pretty accurate with our approximation. Now, so what we're going to do is we're first going to require that f of c is the exact same as our polynomial at c. All right, so those values are the same. Now that's cool. That's good. That's a good place to start. The only problem with that is there are just a ton of ways we can do this. You can come in like this with a straight line. You can come in like that with a straight line. You can do a parabola. You can do something that looks like this. I mean, there's just an infinite number of functions, even polynomials, that will go through that point. So what can we do then? Well, we're going to do something else. Let's start with a first degree polynomial, and we're going to require that f prime of c equals p prime of c. What does this mean? This means that the slope of the tangent lines have to be the same at c. So now what does this give us? This gives us a line. And we can see that for this particular function, this is a decent, it's a decent approximation from there to there. Okay. But you might be thinking, well, what if we, instead of just having a first degree approximation, what if we continued this process? So here's what we're going to do. We're going to not only require, we're not only going to have a first degree approximation, all right, we're going to require this. We're going to require that f prime double prime of c equals Pn double prime of c, all right? And what if we continue this up to whatever our nth derivative is? Okay. Do we continue getting these, a better accuracy? And the answer is usually. So here's what I want to do. I have an example that I've conveniently got worked up here. And let me clear this. All right. There is f of x equals e to the x. And we're going to approximate this function near 0 here, around x equals 0. Now, if I did a first degree approximation and required equality at those derivatives like that, that green line would be, that's our, this would be our approximation. And it's pretty good right in there. All right. Well, what if we went to a second degree function and required equality at both derivatives? I've got to quit annotating. All right. Now look where that is. We've opened up. We're pretty good, basically from -1/2 out to a little more than a half. And if we do a third degree, we see that now we're getting closer. All right. What about a fourth degree? All right. This is a fourth degree polynomial, and it agrees with the function e to the x at 0 for all 4 of those derivatives. And you can see that it's really just very close. And then if we go to fifth derivative, it's even closer. We're getting pretty much on the top right, we're perfect. And then as we get down to about 1.5, and then so we go to the sixth degree, I believe. Yeah. Sixth degree, we are almost perfect from -2 up to something on the right side. All right. So all I've done is that I have gone through and I have found these nth degree polynomials that agree at the derivatives. So in other words, I did exactly what I said we were going to do. Oh, it's gone. Okay, that's fine. Okay, I can bring it back. So I did exactly what I said here. I'm going to require equality at all of those derivatives at the point C, and I have a polynomial that fits those requirements. And then you see that I'm getting pretty good approximations. All right, so this idea is valid. Now, how do I come up with those approximations? And that's what we're going to start with today. All right. Now, here's what I think is just beautiful about this, is that this, I'm going to put myself right in the middle there. This does not require anything special. All right. So in this first line here, what I have a generic nth degree polynomial. I have a constant plus a1 x minus c plus a2 x minus c squared plus a3 x minus c to the third, and so on. And what I did is I took the derivative of that. Now, I'm going to fix one thing here. I'm going to, where's the eraser? I'm going to erase these little blue lines. All right. Okay. So annotate. I can do this though. Spotlight. All right. So you can see that x minus c squared there. All right. So then I took the derivative. Well, what's the derivative of a constant like a sub 0? Well, it's just 0. What's the derivative of a1 times x minus c? Well, it's just a1. So it's all power rule. Derivative of a sub 2 times x minus c squared is 2a2 x minus c. The derivative of a3 x minus c third, it's 3 that. Okay, so then I took another derivative. Well, this first a1, that's just a constant, so the derivative of that's going to be nothing. Then I'm going to have 2a2 plus 3 times 2a3, and so on. And tell you what, let's do one more. I didn't write it in, but let's do what the third derivative would look like. P third derivative sub n of x is going to be, well, the derivative of 2a2 is going to be 0 plus 3 times 2a3, all right, plus 4 times 3 times 2x minus c plus n minus 1 n minus 2 a sub n. That should be a sub n. Right. A sub n x minus c to the n minus 3. All right, look what's happening. In every case, we're getting things, and look what these coefficients are starting to do. 3 times 2, 4 times 3 times 2, n times n minus 1 times n minus 2. And in fact, if you look at the last one, the nth one, you're going to get n times n minus 1, n minus 2 times 3 times 2. This is n factorial. All right. So now what I want to do, this is just any polynomial. There's nothing special. This is just a generic polynomial. So what happens if we evaluate this polynomials at C? Okay, if you evaluate this first one at C, all of this mess is gone. If you evaluate the first derivative at C, anything with an x minus c in it is gone. If you evaluate the third one at C, and the fourth one at C, and this nth one at C, then look what happens. All we're left with are the coefficients. Now, again, all of this is just generic. There's nothing special about it. This is for any polynomial, you would get this truth. So in general, the nth derivative evaluated at C, which is the center, we'll call it, is going to be n factorial times that. All right, and that's true for any polynomial. You know, the nth derivative at C is just going to be that n factorial times the nth coefficient. All right. So page 2. So in general, we have this. Well, what does this mean? This means that in general, well, let's think about this. Our goal was to write a polynomial that agreed with the derivatives, all right, of a function at values of C. All right, well, therefore, if these are my derivatives, you know, this is the values, let me start that sentence over. The values of my derivatives at C for the polynomial will be that. If I'm requiring equality, well, then what I can do is say this, f prime, or sorry, fn of C, right? If I'm wanting equality at all of these things, then in my particular case, for the polynomial I'm wanting to write, this has to be true also. And then just a little bit of algebra brings us this. A sub n then has to be the nth derivative evaluated at C over n factorial. Now, this may not seem like we've done much, but what we have just done is for any function that we are wanting to approximate by a polynomial, this right here, that's what our coefficients look like in that polynomial. So we've actually just, by using nothing special other than what a polynomial looks like and our requirements that we have equality at the derivatives of C, of the derivatives at C rather. This is what our derivatives, I mean, this is what our coefficients have to look like. And that's really cool. So here's what that means. if we wanted to approximate it by a polynomial, then we'll call it t sub n of x is going to be f n of c divided by n factorial x minus c to the n. This is called the nth Taylor polynomial. And this would be what we use to establish our polynomial. Now, this does require one convention to use this notation. We have to define 0 factorial equal to 1. And actually, we do that in general fact. We say that 0 factorial is equal to 1. And there are reasons for that. Basically, the reason is because we have said it so. In mathematics, if there is something that does not really have a defined meaning, we can make it mean whatever we want to, as long as it's the most useful meaning that exists. It's called a convention. And that convention is that 0 factorial is 1. All right, so if you were to expand this out, here's what it looks like. It's f of c plus f prime of c x minus c plus f double prime of c over 2 factorial x minus c squared plus dot 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 plus, f n of c n factorial x minus c to the n. I know I got really ugly there, but this is where we'll pick up. I just wanted to show you where this came from because I thought it's really cool. There's also a good video by 3 Blue, 1 Brown that I will put up, and it's very visual. It doesn't get into the notation behind it, but it gets into the idea behind it, which is really cool. So that's all I'm going to do in this video. And the real videos will start next, and we'll actually do some problems.